Hello everyone and welcome to today's graph reading group session in the Learning on Graphs and Geometry reading group. I'm Hannes Sterk, a machine learning research intern at MIT, and I'll be hosting today's presentation alongside Dominique.
Hi everyone, I am Dominique Biaini, a lead researcher in graph neural network at Valence Discovery, where we use machine learning to empower drug discovery.
Today, Tianlong Chen joins us in discussing his paper, A Unified Lottery Ticket Hypothesis for GNNs, and you can join our reading group sessions yourselves with the link in the description, where you can also follow our socials, and don't forget to subscribe for more of these videos. Do you want to introduce yourself, or should I go with my quick introduction?
Yeah, I can introduce myself. Thanks.
All right, then let's go.
Okay. Hi, everyone. Yeah, I'm Tianlong Chen, fourth year PhD student from University of Texas at Austin. So, and thank you very much for Hannes to invite me to share our recent works. Basically, I think today is a chance to discuss together about lottery ticket hypothesis, especially its applications or its extensions in the graph neural network. So it's very fun and interesting to me. Yeah. So yeah, I will directly start my theory. And this work is published in the ICML 2021. And this work is also credited to my collaborators. They are from the University of Science and Technology of China and AWS Deep Learning. And today I will share this paper following this agenda. Basically, I summarize the stuffs into motivation, technical innovations, some findings and methodology. And in the end, I will share more experimental results and observations. And also, I also include some results out of the paper, but highly related, so we can discuss. And if you have any questions, just be free to interrupt me and we can discuss. Okay. So some motivation about like sparsifies graph or sparsifies graph neural network, I think it's pretty clear. So basically with graph like growing in terms of both size and in terms of both the scale of the graph neural network, which means going deeper, wider, larger, then the training and inference of graph neural networks on large-scale graphs become increasingly expensive, or like increasing training inference time, flops, cost. And also within this inference or training stage, the graph feature aggregations, it is the dominant one which cost massive computations. Since once the graph is super large and complicated, you need to aggregate information or features from all the neighborhood. So then question naturally comes out, how can we to be more saving, obtain more savings? How can we shrink the size of the graph, shrink the size of the GNNs? And another better goal will be to what extent could we co-specify, co-shrink the input graph and the models? Then we can obtain a better or ultra efficiency for GNN or whatever for the inference or the training, ideally. However, for the lottery ticket, this paper mainly focus on the efficient GNN inference. Okay, so in order to answer these questions, in order to satisfy this practical requirement, like we try to design several algorithms or extend this popular lottery tickets idea or concept into GNN domain. So basically, in this paper, the main contribution will be propose end-to-end optimization framework, and such framework can unify sparse, the graph topology, and the GNN model weights simultaneously, and lead to a sparse graph, sparse GNN in the end for better inference efficiency. So, and when you apply this unified GNN specification, I will short-term it as UGS. We do observe a lot of interesting findings, but I will skip this slide and go back here later. I will directly introduce some background of notations about this method. So so before we introduce detailed methodology, I will share some definitions which of the graph lottery tickets or sparse, the combo of sparse graph and sparse GNN produced by our algorithm. I would say this is a little bit different. I would say this is a little bit different compared to the original lottery tickets process. Okay, hi Hannes, I think you raised your hand.
Yeah, so do you right now want to introduce the lottery ticket hypothesis itself, or do you already want to talk about it related to graphs? Because I think it would be interesting to have a few words about just what the lottery ticket hypothesis itself is like, yeah, for a usual neural network.
Great, thanks. Yeah, I forgot that one. I directly go to the graph lottery tickets process. Okay, let me introduce a little bit about the lottery tickets process. So basically, in the previous pruning community, when you prune a large model to lead to a sparse model, people will usually fine-tune from the dense model weights, which means fine-tune from last epoch weights to recover the performance. So this is a traditional method in the pruning community. And people also find that if you didn't use the last epoch weight, didn't use the dense model converged weight, if you just train from the random initialization, it will be very hard to train and very hard to cover the full model performance. And this common sense hold until the 2019, the lottery tickets paper comes out. So lottery tickets paper, they argue that there is a way, a very simple way, but very effective. It will allow you to training the sparse network from random initialization from scratch. So this is the main point the lottery tickets paper want to convey. And the detailed lottery tickets process is like this. So they hypothesize that for a dense neural network, it always it most likely existing some sparse network, and such highly sparse or extreme sparse network can training from random initialization to cover the full model, the dense model performance with less iterations. And such random initialization should be the same as dense models initialization. So basically this hypothesis reveal a very interesting phenomenon, which means in every dense network you have, so existing sparse network, it have undamaged trainability and expressiveness, which means extrainability means it can easily train just like dense model. It will not suffer from worse stability issue or the hard to converge. It will not suffer from that. It is the same trainable as dense model. Second one, expressiveness, which means such kind of lottery tickets, sparse mask combined with the random initialization can fully recover the performance achieved by dense model. So basically this hypothesis point out that there is some network with undamaged trainability and expressiveness exist in dense model. Okay. Yeah, cool.
Do I get it right? First of all, we have a network. We initialize it with some set of weights, the set of weights A, and then we train it. Then the weights are changed a bit, and then we prune the weights. So that means we remove maybe ones from which we think that the weights aren't very important. So some weights that we think aren't very important, maybe based on the magnitude of the weights. If they have very low magnitude, we remove the weights and ignore them. And that way we end up with a smaller model, and that's pruning. But now these lottery ticket hypothesis guys went ahead and then said, yeah, let's reset all of the weights to the first initialization, and from the very beginning we ignore these weights for which we later found out, or for which we found out after our first training step, that they will end up being unimportant. And we now remove those in the very beginning, retrain our model, and then we find, yeah, even if we have removed all those weights in the beginning, we still end up with almost the same performance after training. Like, is that the whole thing?
Yeah, exactly. This is a whole detailed pipeline. So you can see that if you didn't use, so the last epoch weights from dense model, it already contains the full information from the data set. So there is no surprise when you fine tune from the last epoch weights, because your last epoch weights already have rich informations, right? So you can easily to cover the full performance. And the most surprising point in the logic process is that you use the same random initialization, which is such random initialization have no information from the data set, and it can train from scratch to recover the full model performance, which cannot did in the previous literature, which cannot did with other initializations. Yeah.
But right, it's not a completely random initialization. It is the random initialization that we used previously to train our network and find out which weights are unimportant with that random initialization.
Yes, so the random initialization, the dense model used for training. So okay. Beginning point, 0 epoch 1, epoch 0, yeah.
Then to me it's clear. So let's maybe get to your graph part. But first of all, what is that line on the screen? Did you draw that, or?
I didn't draw that. I think it's one of the audience draw that.
Yeah. Okay, I think I look into removing that somehow, but feel free to go on.
Okay, thanks. And there are like a lot of papers try to explain why use the same random initialization can recover the full model performance. I can refer you more literatures to explain this phenomenon. Yeah. Okay, let's go back to the graph logic process. So in the previous logic process, you can see that how we define a ladder tickets. Basically, it contains two parts. The first part is a sparse mask M, and the second part is Z random initialization theta 0. So if you have a mask M and you have a initial weight theta 0, you can define ladder tickets. Okay, but it will be different in the graph domain, right? Because in the graph part, the major consuming part should be the graph itself, should be the input. So in order to extend this concept, we use a triple tuple to represent the or define the graph ladder tickets. You can see from this formulation. Basically, we will have a mask G. So the mask G is a sparse indicators indicate in the original graph which connections should be removed, which connection should be maintained. So basically, it is a sparse mask for the graph input. And the second one will be the M theta. M theta will be the usual sparse mask for the network parameters. So basically, it will indicate which element is insignificant, can be pruned, which element is important, should be remain. So basically, it is a binary mask for the network parameters. And the third one will be theta 0. Theta 0, of course, is the Z random initialization dense model, dense graph used. Yeah. Okay, so if we have the mask G, mask theta, and the theta network parameter theta 0, we can define a graph lottery tickets. Okay, how can we obtain such sparse combo of graph and model? Basically, we use a unified graph sparsification algorithm. So this picture or this figure roughly describes the procedure of unified graph sparsification. And I will go to details in the following slides. So you can see that in the beginning, we have a dense connected graph neural network and a dense graph. So we start from sparsification. Basically, in each iteration, we will like according to some learned importance score, we will shrink or eliminate the unnecessary connections in the graph and in the model. So we will lead to a sparse graph and a sparse GNN. So we will iterate this process. And between two iterations, of course, we will reset the model weights to the random initialization theta 0 to obtain lottery tickets. Okay, so let's go to the details about the methodology. So like a graph neural network findings contains two algorithms. The first algorithm is unified GNN sparsification. Basically tell us how to co-sparcify the data input and the GNN model. Second algorithm basically is try to find the graph lottery tickets leveraging such unified GNN sparsification. Okay, so first algorithm is presented in this slide. I will go into some details. You can see that the input of the GNN sparsification should be the dense graph G and the dense model F. F will take the input graph and the theta 0 as initial, then train the model, right? And theta 0 is a GNN initialization. And in order to like prunes model, prunes graph, we also need to initialize two masks, MG0, which is the same as the foregraph topology, and also the M theta 0, which is the same size of your model size. Then you will define several hyperparameters, like it roughly all of them are step size to control the speed of your optimization, to control the convergence rate of your model. So basically, its output should be a funded sparse mask, MG and M theta. They should be the binary mask, right? Ideally. Okay, so we go to the algorithm one by one. Basically, for each iterations, you need to do a feed forward to calculate the loss in the equation 3. So I will later to introduce explain the loss function. Then after feed forward, you will do the backpropagate. Backpropagate first, you update your network parameters as usual. Then you will update the mask. Basically, in order to make the optimization flexible and make all the process differentiable, we will relax the original binary mask into continuous number. So each element in the mask G and mask C, theta now is a continuous number, which indicates the importance score of each element or each edge in the graph. Then you can like just give the job to the gradient, descent. Gradient descent like update the MG and M theta. It will like make the model try to learn the importance, learn whether the neuron, whether the neuron in the network, whether the connections in the graphs are significant or not significant, are important or not important. After that, you can do a hard thresholding or other method to obtain the binary mask from the continuous mask. So I would say there should be a lot of methods that can achieve this point. In our paper, we use the magnitude-based thresholding. Basically, you can also do the sampling, right? You can imagine each learned continuous score will be a probability whether this weight should be remaining. Then you can like perform some Bernoulli sampling to sample whether this is 0 or 1. Okay, hi. I see. Sorry, I see you raise your hand.
You can finish presenting your slide if you're not done.
Okay. Yeah. So give me like a few minutes to finish this slide. So what I want to say is that you have a lot of methods like hard thresholding or like distribution sampling to obtain the final hard thresholded binary mask mg and m theta. Then you can apply it on the graph and the model. Okay, in the end, in the end of this slide, let me introduce a little bit about the loss function. So you can see that the loss function contains 3 items. First item is the utility loss. Basically, it like calculates the cross entropies if you do a classification task of your sparse model and sparse model and sparse input. You want your sparse model performance cannot degrade a lot or cannot hurt. The second item is L1 regularization of your mask, which will like enforce your mask G be more sparse. And the same story is mask theta. The third stone is regularize your mask M theta. Basically, try to make it more sparse. Yeah. Okay, go ahead. Question.
Thank you. So one of my questions is about the pruning algorithm that is used here. So does it work only when the graphs in the test set is the same as the graph in the training set, or can it generalize to different graphs that are from the same distribution, for example?
Yeah, great question. I would say you like directly catch the main point of this paper. So basically, this paper we only do transductive settings, which means the inference graph should be the same as the training graph, but they use different nodes like this. And later recently we like read up a paper submitted to some conference, and we try to deal with inductive settings, which means the training graph and the inference graph are different. So in that setup, we use like a meta learner. Such meta learner will directly give you a prediction, tell you this graph, in this graph, which kind of connections are significant, are not significant. So in our new work, they can transfer from different graphs. But in this paper, you cannot transfer from different graphs, but you can do other kind of transferability study. I will introduce later in this slide. Yeah, thank you for the question. It is a very great question.
It's interesting to see that you're answering that question in a new paper.
Cool.
Another question I would like to ask also is, here you keep only the edges that have magnitude more than a certain value. Does that lead to some of the nodes that are, let's say, very sparse already? So if you have a graph, most of them have strong connectivity, but some of the nodes have lowest connectivity. Can this cause the graph to become really disconnected, or the way that the edges are determined to be more important, it will always assign these more isolated and more sparse nodes a higher weight so that the connection is kept?
Yeah, thanks. And honestly, like we do like print the graph to see some observations. So I think I can like give you a rough answer of your question. So I will answer your question from 2 points. So first point, you can see that in our like algorithm. So this is performance-driven importance learning, or it will use another word. It is learnable saliency score for each connections or each weight. It is not dependent on the original topology, original connection degrees of the graph. So basically, it will remove the edges, which is contributes less to the final performance. So this is when we try to design the algorithm. Second point, whether it will cause the graph be more disconnected. From the observation I observed, I would say, yeah, it may cause some node be disconnected, but most likely it will try to prune the nodes with dense connections. So I don't know why. My explanation, in my opinion, the possible reason is that, so if a node have dense connections, most likely the information may be redundancy from a lot of connections. So which means it will allow the pruning algorithm to shrink several connections, or it will leave to more space for the pruning. If a node it is a single connected, or the connection degree is very, very small, like just 2 connections. So these 2 connections maybe contribute a lot for the performance of prediction this nodes category. So then it may explain a little bit about the visualization, why the nodes which is densely connected are pruned more, and for the nodes which are sparse connected are pruned just prune little. But somehow it will still cause some node be disconnected. Yeah, I don't know why this answers your question.
Yeah, thank you. It answers very well. If we have time, I would like also to ask some questions from the chat.
Oh.
Yeah. So
okay.
Yeah, one of them is, for example, how this work relates to the attention, in the sense that how does the pruning relates to an attention model where the weights of the neighbors are determined by the attention itself?
Okay, yeah, this is a very great question. So basically, you can also like imagine. So these 2 things are quite similar, right? Because just use different like calculation or mechanisms. Like attention, it will like reweight the neighborhood importance, right? And the pruning mask we use here is to learn each edge's importance score and then prunes on significant edges. So it seems like a hard threshold attention, but I would say they deal with 2 different things. So basically, attention, like you can see that it will soft averaging or soft assigns a weight to different connections, and but for the pruning mask, they like want to so the attention purpose most likely is performance driven, and the pruning purpose most likely is efficient driven. So basically, the pruning score will want to learn whether this edge are totally or are most likely insignificant to the final predictions. Then we directly remove it. And so this is the difference between attention and pruning in the motivation level. And the second level, the implementation level. So there is no difference between the attention-based GNN and the raw GNN, right? You can always like apply or attach a mask on the top of the graph topology, right? Even each weight, even there is some weight in the edges, or even there are some like or even there are some weights on the edges, you can still like multiply a binary mask to indicate whether this edge is important or not important. So I think from the implementation perspective, attention-based GNN is the same as normal GNN, right?
Yeah, that kind of brings up the question to me. What if you do some experiments with gut? What if instead of using the MG to prune, what if instead we use the, I don't know, averaged over some layers, the attention coefficients of gut to prune the edges?
Yeah, I think this is a very great question. So basically, although so basically why we use the magnitude value, it is just follows the standard in the logistics literature, the paper, but it's no reason why we cannot use other metrics, other heuristics. For example, you mean average value of the attention scores among the layers. Yeah, we can use that. It may perform better than just the magnitude-based heuristics. I think, and also for other things like facial information mentioned in the channel. Mm-hmm. I think all of these heuristics can work or can even be better than just use a magnitude-based heuristic or criteria. Yeah.
Okay, but then I want to let you move on a little bit. I see we have quite some slides left, and then we can maybe do a few more questions.
Thank you. Okay, let me continue. Yeah. By the way, always thanks for the great question. Yeah, it will like motivate me, motivate us to like think more and try to design a more better algorithm or do a solid work. Yeah. So the second algorithm basically try to find the lot of tickets using or leveraging the unified graph sparsification algorithm we just discussed in the previous slide. It is quite straightforward. Basically, now the only difference from the input will be you will predefine a sparse level, SG or S theta you want to achieve in the end. Then directly you like perform this for loop. If the sparsity is not satisfied, you will continue to satisfy, continue the pruning process. Basically, you sparsify your GNN model and sparsify your graph using the unified graph sparsification algorithms. Then you update the MG, M theta accordingly, because in the UGS, you will learn a soft mask MG, M theta, which indicates the importance of each element and each connections. Then you can do hard thresholding. You can do sampling or other method to produce the binary mask MG and M theta. And the next step is rewind this GN weight to the theta 0. Then rewind this mask to the also to the initialization. Then you end the loop, and you can produce a sparse model, sparse graph set with the predefined sparse level SG and S theta. Sorry, yeah, go ahead.
Are the masks really completely free after we've initialized them? So are they really completely real values and our gradients can update them any way they want?
Yeah. So in the previous slide, it will relax to a continuous number. Yes, they are pretty free. So we use sorry. So we use magnitude-based hard threshold. Yeah. If we want to use the probability-based sampling, we also need to constrain each mask element within 0 and 1 continuous range. Because in that method, each element in the continuous elements in the mask represent a probability whether your elements should be whether your elements or whether your whether the age should be maintained or not maintained. So in that method, you need to constrain the elements value within 0 and 1 continuous number.
What about instead of pruning based on this mask? What if we instead just completely rewire the whole graph? Like you add edges potentially.
Yeah. So honestly, in the real implementation, we already did that. So basically, if you prune the graph, then we directly delete the graph in the adjacent matrix or in the linked list. Yeah.
Okay.
So basically, you directly change the graph.
Yeah, and you tried that and it didn't work at all.
No, it works. It's the same, right? So basically, you like use importance score from the mask to directly modify your graph. It will be the same when you apply the 0 and 1 mask into the topology for calculation.
But I meant, how does it compare to just using the original graph, for example?
Oh, you mean how to compare with the sparse graph and the original graph, right? Yeah. So so basically it mainly described in the results. I will show it later.
Oh,
is that okay?
Yeah, I didn't know that you also have those results. Nice.
Yeah, thanks. So basically, and also Hannes indicate a very great question. So like in this paper, we only do pruning, right? So basically, if you want to try to modify the graph structure, you can basically you only did one operation, which means one kind of operation, which means delete the edges. So how about we can also grow back some edges? So it will lead to a dynamic growing and pruning for the graph architecture. Yeah, but this is not included in the in this paper. Okay, let's continue. Okay, then I want to show the results we obtained or present in this paper. We did a few tasks like node classification or link predictions. Try several dataset and GNN models like GCN, GIN, GAT, dataset like Cora, Citeseer, PubMed, a very famous benchmark, and some open OGBN, open graph benchmark dataset like pretense, like archives. And all the results, I follow the same format to present the detailed numbers. So let me introduce the format a little bit. So x-axis is the graph sparsity we achieve. And the y-axis is accuracy we achieve. And the first column, first row is corresponding to the second row. Basically, second row just describes the performance and the inference max trade-off. And the first row describes accuracy and the graph sparsity trade-off. But each node are corresponding to each other. Yeah. So and in the curves, we have a few baselines. For example, the dash black line, it is the dense model with the dense graph. And for the blue line, it is the sparse model and the sparse graph produced by our algorithm. And for the orange line, it is a random prune network and a random prune models. And for the blue line, it will be another baseline prune graph with ADMM algorithm. Yeah, Hannes, go ahead.
Can you maybe quickly explain again the max? What are MAT?
Okay, so basically, usually in order to measure the efficiency of the network, we will use the flops or the max to indicate that. they are basically the number of the float calculation in the network inference. So flops means how many plus, addition or the multiplication performed in the network computing. It will like calculate the number of the flops, number of the multiplication, and the number of the addition operation you used in the network prediction to indicate your efficiency. And for the inference max, it is just calculated. I think it should be just calculated the multiplication part. And roughly we will see flops is 2 times the max usually. Yeah, is that clear? It should be a metric for the inference measurement, for the efficiency measurement.
Yeah. So here in the top row, we only see basically a benefit or an improvement in efficiency based on the graph. Like if we remove edges, we could remove as many weights as we want. It wouldn't improve or we wouldn't go further to the right. That's removing edges and weights. That's only captured in the bottom row.
Sorry for the confusion. Let me explain it again. So basically, things like there is 3 matrix we can present in the x-axis. We can present it as graph sparsity or GNN model sparsity or inference max matrix. But due to the limited space in the paper, I only include the graph sparsity and the inference max matrix in the main text and leave to the graph sparsity in the supplementary. So, and for each point here, we are simultaneously prunes the graph and the model. So basically, for example, for the first point here, it is exactly the same as the first point in the second row of the figure. So they are the same model, but just present the result use different x-axis. So I don't know whether it is clear. So basically, for the first point, for second point, it is simultaneously prunes the graph and prunes the model. Basically, it like have 5% graph sparsity. It have 20% model sparsity, but I didn't show it in the x-axis.
I think it's clear. Yeah.
Okay. Thanks.
Thanks.
Cool. Let's continue. So basically, you can see that like for the GCN in the Cora, like it can like achieve like 20%, around 20% graph sparsity. And for the GNN, it is just a few, just a 5% graph sparsity, and the accuracy will not drop compared to the dense model, dense graph. Yeah, and it is not very significant in terms of the graph sparsity. But when we go to the GAT, like it can reach like almost 50% or 40% or 50% graph sparsity, which means you can like remove almost a half connections in your original graph and achieve a non-damaged, achieve a matched performance compared to the dense graph, compared to the dense model. Yeah, and for the inference max perspective, due to the graph aggregation is like costful, and the dense model is also costful. If you simultaneously sparsify your graph and model, even the sparsity is not very large, you can still obtain very good flop saving, inference flop saving. Yeah, and especially impressive in the GAT model. Since GAT model, you can almost like remove half of your graph connections, and this will map into almost like 80% or 70% weights in the GNN models. So by remove a lot, like such connections and model weights, you can achieve like almost 80% flops savings or max savings. Yeah. And we also like conduct a result on the Citeseer. It will give you a little bit different observations, because in the Citeseer and the PubMed, cell graph are more are larger, and average degree are a little bit higher. Then you can see that even for the GN and the GIN, they can reach a pretty good sparsity, graph sparsity, 50% or almost 60%. Yeah. So we go through the link prediction task, because I would say the node classification and link prediction task, say, in my mind, they pretty like the primordial relationship in optimization. So we also test on the link prediction task, and you can see that the observation, the benefits are also consistent, and they also show a large performance margin when you go to the GIN and GAT models. And also they can find the graph ladder tickets and find the sparse model, sparse graph can give you matched performance at a very non-trivial sparsity. Yeah, go ahead.
Thanks for the presenting the results. It's very clear, and you have lots of studies to explain like what's going on. And I think one of the things that's most noticeable is that GAT is not only about like not having a decrease in performance with the sparsity. It's even with your pruning, you have a strong increase in the expressivity of the network and in the results. But even with the random pruning, you can randomly prune more than 50% of the graph, or like you can randomly prune maybe 30 to 50% of the graph without seeing any decline in performance. And I think this highlights like a bit how GAT works in some sense. Like GAT only needs a few nodes to be able to make a decision, because anyways it uses a softmax to decide which neighbors is the most important, so that even if you remove some random connections, GAT can still learn to infer what it needs from the rest. But also what's impressive is that with your pruning, GAT is also better. And I think this goes back to one of the comments in the chat, that can this method help improve graph quality? And do you think, in your opinion, that by using your method, you remove noisy edges from the graph, or does it only help because it's easier for GAT to make a decision? Like, do you have an idea of what's going on here?
Yeah, very good question. Yeah, so yeah, this question, honestly, I think it before. Yeah, so let me answer the question like from two perspectives. The first perspective is for the performance perspective. Second perspective, well, for the graph itself and the graph quality perspective. So for the first perspective, from the result, you can see that not only for the GAT, for the GIN and the GCN also have slightly performance like benefits. Also, although they are not very significant, GAT give you a better, most significant improvement from sparsity. So for the sparsity perspective, I would say, of course, there are also like consistent observations in the computation field, neural language processing field, reinforcement learning field, or other lot of fields that if you like enforce a sparsity constraint, which means you remove some insignificant neurons, sorry, insignificant connections or insignificant neurons, actually like you post sparse regularization for your model learning, since the performance can be better. So these regularizations roughly can explain in several ways. For example, it like reduce the sample complexity and the benefits to the generalizations. For example, prune the critical architecture like can serve as an inductive bias to help your model learning better, or learning converge quicker, learning better. So there are a lot of possible experimentations to explain why your like remove some redundancy part or enforce sparsity actually apply a regularization to your model learning and get performance boost. And the second perspective for the model graph quality part. I think this is very makes sense and very intriguing or interesting directions to explore whether we can use such kind of method to improve the graph quality. I think from my perspective, okay, in my opinion, I think the answer is yes. And I also like do some visualization in this work and in another work, I mean, just submit to some conference. Like we observe that maybe take an example, take an image as an example. So like Dr. Hinton, they published a paper to modeling an image into a graph, right? And we like do some visualizations in that graph. So we can see that if we like perform such kind of pruning, it can eliminate a lot of redundant connections in the background of the image. And then it will remain the critical connections which are circumstant or which are like covers main object in the image. So this will be a very illustrative example to tell us such pruning method can indeed shrink some redundant or useless or even harmful connections or noisy connections in the graph data and maintains a critical part. And I didn't like examine this visualization or examine these findings in other graphs, like some protein graph or some social network graphs, because I think in that part it is hard to define which connections or which node are noisy, are harmful, because we can only see from the performance, right, whether this is harmful or redundant. But from the image experiment, we can observe, we can visualize the image, whether the edges in the background, which is useless, are removed, whether the edges circumstant or covers the main object are maintained. Okay. I don't know whether this answers your question or rather produce more questions. Yeah, thanks. Yeah, I think this is a very good question and it's worth to explore later. Yeah. Okay, let me continue. I think there is only 5 minutes left. Let me go through the rest of the results. So basically, we also conduct on the large graph, like OGBN archive, OGBN protein, and OGBN collab. We can obtain consistent observations which support our method can scale up to large graph and to deep graph neural network. It is not trivial in the logistics domain, because in the previous logistics paper, this hypothesis only valid for small models and small data set. And later, a lot of new techniques invented, like weight rewinding or other techniques, I will not include it here, to help the logistics scale up to the large model and large data set. And in this paper, we found by using our proposed unified sparse sparse graph sparsification itself can directly scale up to large models and large graphs and achieve good performance, good efficiency in terms of the inference max or flops. And we also try different initializations. Previously, in the previous old results, we tried a random initialization, and we can also use other published or released pre-trained GNN model, right? We can use some. Here we investigate the pre-trained models from GraphCL, and we can see that the initialization itself also make a lot of contributions to the performance or achieve the sparsity. And in the end, I want to share a little bit about the transfer studies, and also asked by the audience previously. And this is not included in the paper, but included in the rebuttal part. And you can also find the detailed explanations in the SML website. I think they included the rebuttal document. I'm not sure, yeah. But let me introduce it here. Basically, as mentioned previously, we cannot do graph transfer in this paper. So, but what kind of other transfer we can do? For example, we can do task transfer. Basically, we can use the mask prune from node classification, directly apply it to the link prediction task. So you do not need to find a graph, find the mask again for a new task. And the second part is we can do GNN level transfer. Basically, we can find the graph via GCN and transfer the mask directly to GIN or GAT. And we can also do pre-train and downstream transfer. Basically, we can identify your mask on the pre-training task. Pre-training task will be GraphCL. So you can transfer directly of the sparse mask you find on pre-training to the downstream link prediction or node classification task. Yeah, and this is a performance comparison of you only prunes the model and prunes the model and the graph together. So we can see that the prunes the model and the graph together indeed can give you a better performance and efficient trade-off and a better performance. So a possible explanation is that I would say the graph part and the model part, basically they should keep a rough balance. So if you use a very large graph, but you only have an extreme sparse model, like just a few neurons, I think this is not enough to learn a meaningful mappings. This is why you only prune the model, the performance will degrade a lot. Yeah. Okay, I think that's all. Thank you. Yeah, thank you for the listening and thank you for the invitation.
No,
any questions?
Thank you for the awesome presentation and for the nice paper. But yeah, about questions, I would have gotten, if you can go back to the previous slide. There, yeah, you're basically showing that the UGS is doing better than if we just do a lottery ticket hypothesis on the network and only prune weights, right? Yeah. Okay, and we also had another question in the chat about what parts of the pruning are the most valuable in what situation. So when is the graph pruning and when is the weight pruning more important? So this kind of already goes into that direction, the results that you're showing here. But can you, do you have more insights on that?
You mean which part is more valuable? What does it mean? It means which one can give us more benefits to the performance and inference efficiency?
Yeah.
Yeah. Okay. So, which part can give us a better performance? Honestly, I didn't do a very extensive study about which part can give you better performance. From there, we can only see that the performance gain from the model and the graph, they are not overlapped they are somehow like independent. You can combine them, combine the model sparsity and the data sparsity can lead to a better performance. And for the inference part, I would say, for the inference part, I would say, yeah, it is also hard to like say that, but model pruning itself can also like lead to a very significant flop savings. Since if you shrink the model, older like node aggregations will be a sparse matrix times a sparse matrix rather than sparse matrix times a dense matrix, and this will give you a lot of flop saving. And for the graph sparsity part, basically, sorry, I don't think I like have a very accurate answer to this question. Which part like contribute more? Sorry for that, but I can like do more like experiment to further explore that and maybe give you an answer later. Is that okay?
Yeah, okay, but I guess for our case, kind of like usually or oftentimes, I think at least the important thing is to get smaller models and to prune weights to have the models fit onto some device that it otherwise might not fit on. But here we're actually more interested in floating point operations or max that we're doing. So the edge pruning becomes very important, right?
Yeah. So I would say the graph. Why we consider graph in this paper or this graph neural network domains. From my perspective, I have two reasons. First reason is that because graph aggregation part is consuming, it is different like computer vision models or NLP models. Second part is that we can also like shrink or identify the crucial part in the graph itself. It may offer you some iterability. So which parts, which nodes, or which connections is important in the prediction. So it may offer you some iterability benefits. Yeah, but yeah, okay, thanks.
So in this way, the problem is kind of different for GNNs than it is for other, I don't know, language models or just CNNs. Okay, but
yeah.
Thanks for the answers.
Thanks, Dennis. Yeah, I also see like a lot of questions in the audience. Yeah, please go ahead.
Johannes, do you maybe want to?
Sure. And thanks for the great talk. Very interesting work.
Thank you.
I saw in the paper that you used the ADMM optimizer. I hadn't heard of it before. Do you have an insight on how this impacts your results? Like, do you expect similar results for the more standard Adam optimizer, or why do you choose this one?
Okay. Yeah. Sorry for the missing. Basically, I should like explain this baseline more. So basically, ADMM here is sparsification framework rather than optimizer. So ADMM here like so of course ADMM itself is an optimization framework. Basically, we found a literature like a paper that they use this optimization framework to sparsify your graph. And in that paper, they like only consider sparsifies graph topologies, graph edges, and within I formulate it as ADMM optimization problem, and solve it by the ADMM algorithm. But so you can imagine this will be another baseline which do the graph sparsification. Yeah.
So would you agree that when trying to sparsify a graph, one should always use ADMM and not resort to more standard optimized? Like, does this seem strictly better?
Well, ADMM is not an optimizer in this case, right?
Oh.
Tianlong?
Yeah, it's Yeah,
just,
it is.
it's just another pruning method.
Yeah.
Like instead of pruning based on the magnitude, we prune with this ADMM method, right?
Yeah. Yes. So you can see that basically we use L1 constraint to enforce the sparsity of your mask, and ADMM basically it will like do the variable splitting and use alternative descent. It will first introduce dual variables to like dual variables to like put your constraints in the objective functions. Second step, it will split the variables into multiple group. Third step will perform alternative optimization step to each group of vectors. In the end, it will produce a sparse mask in that paper. And I think I can share you the literature through email. Maybe I will send it to the Hannes. Hannes can help me to forward.
Already in the chat.
Okay.
Oh, nice. Thanks. I'll take a look.
Yeah.
Really, I don't know enough. Thank you.
It's okay. Yeah. Thank you. Cool.
Thanks for the great presentation. One thing I really liked about the paper is how much results and how much empirical results and ablation studies you have. But one thing I was wondering if you tested is whether when you try the pruning of the graph, the pruning of the sparsity of the graph many times, does it give you the same, with different random seed, does it give you a similar pruning or does it give you different pruning?
Okay, yeah, very, very great questions. So unfortunately, we didn't show the mask overlap. So your question will be whether different random seed, whether different random start, it will produce different masks, or how the masks are overlapped with each other, which kind of how many percent are like in common from different random seed, right? So unfortunately, we didn't show the overlap study in this paper, but in all other like logistics paper, we always show the mask overlap. So from my experience, but honestly, I did a few like studies on the Cora dataset because this is much more cheaper. I can run a lot of times, right? And we see that like if you like give a 50% sparsity ratio, which means 50% edges are pruned, 50% edges are remaining. I remember it were like also 60% or 50% of the remaining edges are common from 2 to 3 random seed repetitive experiment. So let me rephrase my answer. If you use different random seed to generate the mask, I would say half of them or most of them, most of the remaining connections are the same across or are shared across different random seed, and some of them are different. Yeah, and if you like choose different graph sparsity, this overlap ratio or common ratio may be different. It should be a curve like this. So a curve like this. Yeah. Is that answer your question?
Yeah, it answers very well, and it's interesting to note that. So about half of them stay the same, meaning that the network really learns which connections are the most important, and in most cases, the most important connection are the same. But one thing I would like to ask here, it's something you probably didn't try, but kind of a repurposing of what you did, but as a model instead, just as a way of reducing the weights. In some of my previous papers on graph neural networks, one thing that we show is that using a single aggregation, like using only mean aggregation or max aggregation or sum aggregation, lacks lacks a lot of information about the graph, and that using many of them is actually more beneficial. And actually what we show is that both theoretically and empirically, having different masks that are uncorrelated with each other is an efficient way of doing aggregation. So here my question is about, like, suppose you take your method to prune a graph 90%, and even if the results decrease, could you then take this 90% and assign it as a constant aggregator, and then take back the GCN and GIN as a parallel aggregator, and re-prune that second model to obtain a different mask that is uncorrelated with the first mask, such that both together give more important results?
Yeah. I think this suggestion is super interesting. And honestly, I did almost same idea in the computer vision field. And its paper is published in the iClear 2020 called Lifelong Lottery Tickets Process. So I don't know. Let me just search it. You can see my screen, right?
Yeah.
Can you see my screen? Okay. Lottery tickets systems. Let me see. Yeah, this one. And first, I think you are correct. I think that one can gradually identify the crucial part in the graph, and first you identify the most important 10% for aggregation, parallel aggregation. Second, you can identify another crucial connectivities from the candidate pool. And we did similar things in the computer vision field, lifelong learning scheme. So you can see that in this pipeline, lifelong learning, basically you will have a lot of tasks sequentially arrived. So you can see that for the first task arrived, we prune the elements, prune the model, and just left the critical path in the model, just a few. Then we maintain this part unchanged. Then when you meet the second task, you can perform the pruning from dense to sparse. You can find a new crucial connectivity patterns like this. Then you can union the first part and second part together. Then for the third task comes here. You can also find a new critical path, which contributes a lot to the performance. You can add this path to the previous set together. Then you can gradually identify the crucial components. But this is conducted in the model, and your point is conducted on the graph. Yeah, I think you are right. I think this motivation are very interesting, and I think it should be work. Yeah.
Yeah, thank you. That's a very interesting paper. It seems to be very interesting. Could you share the link in the chat if possible?
Sure.
And have you already heard of this inductive lottery ticket learning for graph neural networks paper?
Yeah.
Vaguely, okay.
Yeah, I heard that, but I cannot answer your question. Yeah.
Okay, I guess that's enough. It's just a related paper. Good.
Yeah.
But then I also would have had the question, you find, in the paper we find that GAT is better for edge pruning. So if we prune the edges, GAT is doing better than the rest. Do you think GAT is only doing better because of the edge pruning and because the edge pruning is starting to hurt the other graph neural networks? Or do you think GAT can also better deal with the weight pruning? Do you know what I mean?
You want to say whether you want to say that you want to question that the benefits of the GARDs compared to the GIN and GCN are they like from the pruning model or pruning graph? Is that your question?
Yeah. So is GAD more resilient only to edge pruning or also to weight pruning?
Yeah. So in order to like answer your question, basically, I think the experiment I want to show is that you only do the model pruning and only do the weight pruning for the GCN, GIN, and GAD, right? And unfortunately, we didn't do that. My intuition is that so this is just my guess or my understanding, but it may be wrong, maybe inaccurate since I didn't do the experiment. And my intuition is that I think GARD is more amenable for the edge pruning, yeah, rather than the model pruning. So, but this is just my guess, yeah.
Yeah, like that's the intuitive thing, right? But it would have been interesting to see it confirmed. Okay.
Yeah, I agree. So it will be very interesting whether the model part GAD is also amenable too. So this will indicate that your like aggregation method or your data part will indeed influence your model pruning resistance. Yeah, I think so. I think this is interesting. Yeah.
Okay, but in your paper, you also have these observations, and in observation 5, you write denser graphs are more resilient to sparsification. And like when I read the text under that, it sounded to me like you're trying to say that if we have a denser graph, we can't prune it as much. But that's not correct, right? If we have a denser graph, we can prune it more without losing performance. Which one is the correct one?
Okay, so I will say the GARDs is more amenable for the sparsification, which means compared to the GARDs to the other like GNNs for the GIN, GCN. So GARDs can lead to a very large.
Yeah, okay, but now I'm talking about graphs. If we have a denser or a less dense graph, which one is more amenable to pruning, so to say?
I think I need to check the statistics in the paper. I think it's dense graph are more amenable to the pruning, right? Because it may have more redundant connections. So which means I think the graph like have larger average degrees for each node, which means more denser.
Yeah, that's the intuitive thing, right? Yeah. I just understood the opposite when reading the observation 5, but I guess I just got that wrong.
Yeah, sorry for the confusion. Yeah.
Yeah. Okay. But if there are no other questions in the chat, in some sense, this also indicates that GAD is more resilient to noise in the graph. Yeah, we've also seen some evidence for that in other papers, like the GAD V2 paper, where they show that if you have a GCN, then it's the least resilient to noisy edges. If you have GAD, it's a bit more resilient. And then if you have GAD V2 with truly dynamic attention, then you're really resilient to noisy edges. Okay. But then I want to thank you very much for your awesome paper and for taking time to present it to us and answering all of our questions. Do you want to say some last words?
Yeah. First, thank you for the invitation. Yeah. I think this is very interesting and very helpful to discuss with you guys, like in a meeting or in a paper sharing. Yeah. I think it gave me a lot of like ideas, I can try it later. Yeah. And thank you for all the interesting questions. And if you like, if you guys like discuss more, we can like organize some offline discussions for all the research ideas or for the other new stuffs. Yeah. Thank you, everyone. Thank you, Hannes.
Maybe if you want, you can join our Slack and then you can discuss in the discussion channel there. I'll send you a link in case you don't have that yet.
Sure, it will be perfect. Thank you.
And I will also share all of the papers that you mentioned, as well as the inductive lottery ticket learning for graph neural networks, which might be related to a lot of the questions we brought up during this session. I will share that in the Slack. All right.
Thank you.
Then I definitely learned a lot from this session and from your answers. I think everybody else as well. And in the name of everyone, thank you very much and have a nice day.
Thank you. Have a nice day.
Bye.
Bye-bye.
Thanks again.
Bye-bye. Thank you.
So I really liked this presentation. I learned a lot and I guess you did as well. So many thanks to the great presentation by Tianlong Chen. And don't forget to join our reading group with the link in the description and subscribe to our weekly videos on graph neural networks.